I have found vulnerabilities, but not any vulnerabilities in OpenSSL, so I hope I'm not disappointing anybody here. What I want to talk about here in this presentation is to show how there are a lot of people within the academic research field in cryptography who find some issues that are relevant to cryptographic implementations, including OpenSSL, how we can collaborate, how we can strengthen the ecosystem, and how we can make sure people find each other to improve things. Part of my talk is going to be about cryptographic hash functions. Some of you may have seen these slides before. I'd really like to keep things super basic and explain again what a hash function is to make sure we're all on the same page. So virtually all cryptographic hash functions are iterated hash functions. What that means is that the message, possibly after padding, is going to be split into blocks of a specific fixed size. And then we're going to process every block of the message one by one until we end up with a hash value. When you take this hash value, I add a little fingerprint to it to indicate like this should be a unique thing. So the idea is that when you do, for example, a cryptographic signature, a digital signature, that you don't sign the message, but you sign the hash of the message. And the hash of the message is a fixed length thing that stands in place of the message. If you want to implement a cryptographic hash function, there are two interfaces that are common. One is a one-shot interface, hash, just provide the whole message at once. And then typically, you'll also see an implementation of an interface that allows you to process the message in parts of an arbitrary length. Then you will call first init to initialize a data structure, then any number of times update to process different chunks, and at the end, final to compute the hash. Small question here. Does anybody have an idea where or when you would use this init update final interface? I see Bob Vegas raising his hand. I know you know. So. I see. I see what you're saying. I just want to make sure, like, it is possible to hash a lot of data using either hash or init update final. You just need to make sure the data fits into memory. But if the data doesn't fit into memory, then you have an issue. And actually, as people start to give examples of places where you want to use init update final, a thing that is common among these examples is that often you want to avoid making a temporary copy of some data. So if you're saying, I want to hash AB, ABC, like I want to compute a running hash of a message that keeps getting longer, like a TLS transcript, it can be convenient that you don't need to store these intermediate copies of the entire text to be hashed, but that you can already keep track of what you've hashed so far. So this init update final interface is really helpful to avoid temporary copies. What it is not is that you need to process your message in chunks of this size. Like this size here can be some arbitrary size that makes sense for the application. People cannot see this in the recording, but Bob Beck keeps saying the entire time, yes, 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 yes. So I guess we're on the same page here. OK, so let me discuss some vulnerabilities that can appear when you have implementations of cryptographic hash functions. Here we're looking at the NIST SHA-3 competition. And we used some methodology. My colleagues here were experts in software testing, so it's interesting to collaborate, to try to find bugs in submissions to the NIST SHA-3 competition. Here is a finalist algorithm, one of the 5 that was the finalist, not the one that won. Since 2008, there is a bug that was present in the code. It's like an earlier slide used to say introduced, but then people at NIST told me, no, like that seems it was intentional, so let's just say the bug appeared somewhere. So the bug appeared in 2008. And then in 2015, the bug was disclosed. Once we found the bug, we started looking up. Turned out that the lead designer of Blake, Jean-Philippe Aumasson, who's like the French Bruce Schneier, has now like given presentations to discuss like, hey, we have a serious thing going on. Like there are a lot of bugs that we are not finding. So what happens? Blake, let's take for example Blake 256, processes a message in blocks of 64 bytes. So 64 bytes is the size of the block in the first slide where you saw the blender. If you call init, and then you call update on a block of less than 64 bytes, and then update on a block of exactly 64 bytes, and you do this specific sequence, then what happens is the first call to update is forgotten. So it's as if you didn't make it. So the result of calling init update update final is the same as calling init update final, where you don't do the first block due to a bug in the implementation. So this is bad. When I was discussing this with my colleagues, they were asking me, okay, so if you have two different inputs to your hash function and the output is the same, is that a problem? And I said, yeah, it is a problem. Because like, well, that stands in place of your message for a digital signature. So that's an issue. You would call this, if it's an attack on a cryptographic algorithm, a second pre-image. So like, the algorithm is fine, it's just the implementation, but like still, we want to make sure everything is okay, right? In this case, what you have is you can modify the message, basically leave out the first block, and the hash will remain unchanged. But here, okay, the vulnerability was already found by the designers. So NIST didn't know because the code on the NIST website was not updated, and this was only disclosed after the SHA-3 competition was over. And when I was presenting this to the people working on cryptographic implementations used in the real world, the reaction that I got was like, oh, interesting, but we don't care because that's not actually something we use, right? Find something in an algorithm that we're actually deploying. This was an entry that didn't win the competition. So I thought like, I need to look a bit further. I need to get my own CVE number assigned to me because that will increase my street credibility among the people who are in the field. So I started looking everywhere, and then just by chance stumbled upon the code that Apple Core Crypto was using to do hashing. And yeah, like from a research point of view, it's maybe not that interesting. I just saw the code and I saw immediately that it was wrong. But then went through the reporting procedure. Got my first CVE number assigned, NVD classification, so NIST, the National Vulnerability Database maintained by NIST, 7.5 high. So what happens if you hash a message of at least 4 gigabytes, or do like one call to update that is 4 gigabytes? Then you will enter into an infinite loop. And as it turns out, NIST actually knew about this somehow, because if you look at the documents that describe how hash functions should be tested, it says, well, we only test small messages, because if an implementation is correct for small messages, it is also correct for large messages. So like, sometimes the possible gaps are out in the open when you go through the documentation, right? Well, maybe we should be testing some large messages. So together with Chris Celi, I introduced the NIST Large Data Test, or LDT, basically adding test vectors to the NIST program to check if you can process large messages correctly. And then things become interesting because the labs, it's an optional test, can start to turn on these and see if maybe some interesting stuff is found. And there was. So for example, in a completely unrelated SHA-3 implementation used in GNU-PG, like the open source PGP, a failure of the NIST large data test was found. Here I give the Red Hat bug ID. but also in NSS, Netscape Security Services, the cryptography behind Firefox. Failure was found as well, processing large inputs. For those interested, I provide the Mozilla bug ID here. So it's interesting to see, once you introduce a new test, that's a really effective way of seeing other implementations fail as well, and also showing a bit of value of what the NIST program is actually trying to do. People like to say, oh, the test factors don't matter because we always pass them. Well, maybe we should be adding new test factors to see implementations fail. As I was exploring this topic a little bit further, I didn't want to find more vulnerabilities, but I wanted to show that the winner of the SHA-3 competition, CatShack, which became to be known as SHA-3, was correct implementation. But somehow the tools that I was using to try to show correctness didn't work. It took me a while to figure out why. Oh, the code has a serious vulnerability in it. So here, it's not 7.5 high, it's 9.8 critical. I think it should be 10, but I don't want to discuss too much. What happens here? Let's say that for the implementation of SHA-3, that was by the designers, widely spread, widely available, the one that was part of the submission during the NIST competition. Let's say that you call init, then you call update on small input, it's like some number of bytes, x, less than a block. And then on a really large input, where it has to be 4 gigabytes minus x, and then you call final. Then what happens is there is a buffer overflow, and then I was like, oh, I need to see how serious this is. So I basically froze this type of research and tried to see how can I do like a full exploitation. So it turns out that you can show here that you can do arbitrary code execution. So this would be a scenario where, for example, I give you digital signature. I don't know the secret key. I'm asking you to verify if the signature is correct. You know the private key. But as you're doing the checking, in several algorithms, like at448 does exactly this call of updates, where first you process a few small parts, and then you process whatever is pointing to the whole message. If that update call is going to be one pointing to a large message, then you can provide some code as part of that message, as part of the input, and that will get executed as you do your buffer overflow. We'll start overwriting internal values in your stack. And it's a really interesting type of overflow because typical protection measures, like if you have like stack cookie, stack canary, don't function here because the data, the way that SHA-3 works, is not overwritten into memory, but it's XORed into memory. So if you're XORing 0 values in the places where you want to make sure the stack cookie stays the same, then there's not going to be any impact there. There's also, if you don't do the minus X bytes, an infinite loop that will happen. So it's actually two vulnerabilities in one. There's a buffer overflow with code execution. There's an infinite loop. So I'm going to show the code that contains the mistake, not because it's supposed to be obvious, actually because it's supposed to be like completely non-obvious that there's a mistake here. Usually when I ask, can you tell me which line is wrong? Well, you have a good guess. There are 3 lines. Pick any of the 3. Usually people will say like, this cast to unsigned int, like that looks wrong, right? But it turns out in the final version, in the corrected version, you will still see the cast to unsigned int. So that was like not the problem. Maybe it's a little bit too obvious. What's happening here is that you have a pattern that says if A plus B larger than C, that's basically the second line. And that is not the same as this pattern here, where you have if A larger than C minus B. So mathematicians seem to get really confused by this, because in school we learned that it is the same. Python programmers are confused as well, because in Python it's the same. But not if you do an implementation in a language like C, because whenever you add 2 values, there is a possibility that the addition can overflow. If the addition overflows, in this case, because we're dealing with unsigned values, that's a well-defined operation in C. And C will say, well, I'll just wrap around. But then what will happen is you're expecting to get a really, really large value in your input, but turns out you get a really small value because you overflow. And then this second line will not get executed anymore, and then this will lead you to have the buffer overflow. So as we're correcting the code, the first thing we need to do is to move the minus instance byte iota index to the other side. And then to get rid of this infinite loop, turns out that we actually need to have data byte length minus I here to make sure that we also have the higher order bytes of partial block. That was the cause of the infinite loop. And then to avoid computing partial block twice, so if you want to show the final code that is now in the fixed SHA-3, like you can put the partial block here at the end. So I haven't spoken about OpenSSL yet, and I see people complaining like every talk should be about OpenSSL. Where's OpenSSL coming in? Sorry, here's OpenSSL coming in. People from GitHub Security Lab reached out to me saying, how can we help? This is a really interesting vulnerability. Are there things that we can do? And I said, well, I'm going to be in the Bay Area anyway. Like maybe it's a good idea to see it. Like let's discuss and let's see what we can do to try to find and fix these types of vulnerabilities. So what I ended up doing in collaboration with GitHub Security Lab is write a query in CodeQL describing the vulnerable code pattern that underlies the vulnerability in SHA-3. So basically this pattern where like you add two things, and if it's larger than something, like it's supposed to be a limiting function, but you did the A plus B larger than C instead of the A larger than C minus B type of pattern. And then, well, if you have your own repository on GitHub, you can click on settings, you can click on code scanning, and then this pattern will be detected. If you're working for GitHub Security Lab, you can scan all of GitHub. So as the team was checking to see, well, what's the quality of the query? What are the types of false positive, false negatives? What do we find? They reached back out to me to say, like, hey, you're a cryptographer. Maybe this is interesting. Can you have a look at this code? So this code, as you can see on the second to last line, OpenSSL memcopy, is not OpenSSL. It's actually boring SSL. But there's a similar pattern that appears in OpenSSL as well. So we're doing the same stuff. We have an implementation of HKDF, hash-based key derivation, which you will do if you do a TLS 1.3 connection. And the line where you're trying to do this limiting operation is one that is now rewritten as this. And then you can actually immediately see what the operation is doing. It's just like if to do is too large, to do is equal to that specific value. So this is what I contributed to boring SSL. And if you do an HKDF computation, then this is the new code that you will see in there. The same pattern also appears in OpenSSL. I should mention here that this is not a vulnerability, because you can check if you do a symbolic computation that there are no values where this done plus to do can overflow. But in CodeQL, because you do approximations, you don't know that. So CodeQL has this predicate that is called might possibly overflow. And this predicate turns out to, yes, well, this might possibly overflow, but that actually doesn't. But still, it's helpful, and that's the message I'm trying to send here. It's helpful to not just fix vulnerabilities, but also to help developers to make code easier to read, to make it easier for both humans and tools to see that certain bad things are not happening. And then also reducing the false positive rate of queries, if you want to apply this CodeQL approach. Well, what does the code look like in OpenSSL? Because I had to show what is relevant here to the audience. It looks a bit similar, but because my query was not considering, like there's a question mark missing. So at the end of the line, there should be a question mark. Like this is a compacted if statement. So my query wasn't actually detecting this. It was just detecting if, not like the question mark colon shortened operand thing. Then The same problem happens here, but it's just different names of variables, and it's yeah, I'm not using the if statement, but the 3 operation if additional, yeah. So here in the corrected code, I propose to rewrite the code in this way. You will see that if diglen is limited to this value, then it's equal to this value. And this is one line of code that I contributed to OpenSSL. And that's why I proudly have here the code contributor ribbon on my badge. This refers to the one line that I contributed to OpenSSL, this specific line here. But then this got me excited, right? I was like, oh, I contributed one line. Maybe I can double, triple, quadruple my contribution if I contribute additional lines to OpenSSL. So that's what I wanted to do in follow-up work as I got excited. I should maybe say, because I don't want to build too much suspense, I failed and ended up with just one line of code, the one that you see in the previous slide. But at least I tried. So let's see how I wanted to contribute some more code. There is an issue in OpenSSL that has been reported in 2020 that came as a result of a presentation, academic paper by Benmocha at SEC 2020, I think. Or where does it say 2021? Maybe the issue was open in 2020 and the presentation was given a year later, or maybe I put the date wrong, I have to check. So here, what Benmocha is doing is he's looking at what happens if you use the API for HMAC in new or maybe unexpected ways. That gives you then a strange algorithm that is not actually HMAC, but some different algorithm. And then you can try to see what cryptanalysis attacks you can apply and what different properties it might have. This was reported to OpenSSL, but it's an issue that remained open for many, many years. And my intention was to contribute some extra lines of code and to close the issue. And it's closed now. So what happens here? So for HMAC, there are 2 common HMAC interfaces. So there's one where you call HMAC one shot. And in that case, you it looks the same as what you saw on my earlier slides. Difference is that there's now a secret key that comes in there as well. So HMAC is basically the keyed version of a hash function. It's used to compute a message authentication code, or a MAC. But there's also an interface to use HMAC init X. That's the way it's called in OpenSSL. HMAC init is deprecated. HMAC update, and then finally HMAC final to compute the final HMAC value. So what's the unintended feature here? Well, let's say we call HMAC initialize, HMAC update, HMAC final. And then we call update again and final again. In that case, I don't know, you might wonder, is this being used somewhere? Would it be useful to run update after final? I don't know if anybody has any thoughts on this. Where or when would you use this? Not always, Bob, please. You shouldn't use it. Yeah, exactly. Like when you have, so the response to the audio was, yes, TLS handshake hashes. If you have the need to hash A, B, ABC, like some thing that keeps getting longer, it can actually be convenient if you say, well, I run update after final, because what it does is it's supposed to undo the last final and then continue as if you're computing the hash, the HMAC of a message that keeps getting longer. You could also say, like, well, maybe we shouldn't use this, but the question here is, on the side of OpenSSL, is this, when you see the issue with running init update final, is this something that should be fixed in the code, or is this something that should be disallowed? What to do? There was some discussion about this. If you look up the issue that I showed on the previous slide, Some people were saying, well, this should be disallowed because it leads to a serious security problem. What Gal showed is that for OpenSSL, you can instantly find collisions and even multi-collisions under any keys, like a really bad security vulnerability. You could also say, well, maybe the code should be fixed and this should be officially supported, because there actually do exist some interfaces in OpenSSL where running update after final is a feature. And what it does is it undoes the last final and continues processing the input from there. If you want to look at some of the responses we got in the academic world of how to handle this issue, here's a paper by Sean Ho et al., where it says, well, maybe if you want to make sure you're safe in every possible issue, any sequence of calls that you might do, you could consider, instead of an interface where you have many different states, you need to make sure you don't do a transition from one state to the other that is not allowed, to basically allow any type of call that somebody might do. And then what it would mean is, well, if you forget to call initialize, it initializes itself. If you call update after final, it undoes the last update. And you could consider any call is allowed and give a specific definition to that. And then you don't have to worry about doing a sequence of calls that you are not allowed to do. So this could be perhaps something to consider. Either way, I was set out to increase my contribution count to OpenSSL from more than one line. So I wanted to reproduce first the issue. And it turns out I couldn't. And then I was like, whoa, that's strange. Turns out that since OpenSSL 3.2.0, what I showed here in the previous slide, this attack where you're doing update after final, doesn't work anymore. But the issue is still open, so I was surprised to see, oh, what could have caused this issue suddenly to get resolved? What's actually going on here? It turns out that there's a completely unrelated issue in OpenSSL that unintentionally fixes it. And here, what's happening is something, it's a bit weird, but please give me some time to go through this with you. Do not fail if context duplication does not succeed. What's going on here? So, as I mentioned, there are some APIs that explicitly support calling update after final with intended behavior that undoes the last final. But then what you need to do is when you call final, you need to make a copy of the internal state before applying final, because that's the copy you will need when you call update. So you need to make a copy. If you don't make a copy, then doing update after final can never work. Oh, but it is actually possible if with OpenSSL, because you can use providers, and these providers can be some hardware devices, it is possible that making that copy fails. And then we get a really interesting situation where you call init update final. Final tries to make a copy in case you do another update later, but on certain hardware security modules, that copy fails. And this is not actually a problem you necessarily need to deal with, because if you never call update in the future, there's no issue. You just call init update final. Why? Even if the copy fails, you don't necessarily need to worry about it. It's only if you want to call update afterwards. So what Simo was suggesting here is to say, well, can we maybe delay that failure? Because when we're calling final, it's actually fine to say, well, the copy failed, so don't do update after this, but everything else is okay. We computed a correct HMAC here. So that was the intention. Then the intention was to, indicate, using an additional flag, whether a state has been finalized, and then to indicate, well, some algorithms don't allow you to call update after final, so you're not allowed to call update. Indicating here a solution for the case where final, where you want to solve the issue where the copying of state after final is failing. And as it turns out, that is actually also unintentionally solving the issue that Gal Benmocha pointed out in his academic paper. So I did want to offer a new test vector to basically cement in that new behavior, to show like, well, if you're calling HMAC, then when you call update after final, that is since 3.2 something that will fail. There's a new test added here. If you use older OpenSSL versions, the test will fail. For newer versions, this test will pass, indicating that the update is not possible after final. But that's testing code, right? So the rule seems to be, if your code is if whatever code lines you contribute is in the README file, if it's in test code, that doesn't really count. So I consider myself still to be at one line of code. But I hope to be back next year with maybe some additional lines. Let's see. So let me here conclude my talk to allow a lot of time for questions. So basically, I discussed two main parts of OpenSSL and gave a bit of an insight into issues that can appear. Try to encourage people who have an academic background to reach out to the team of OpenSSL, of other cryptographic libraries, to work together and fix issues when we find them, not just to say, okay, we stop at an academic paper and then we get our PhD, but actually try to see how to help, how to contribute, how to be part of the ecosystem. I focused on HKDF, hash-based Key Derivation Function, which is part of the TLS handshake, where there is one line of code that I contributed, a line of code that you will execute every time you go to a secure website, but not a bug, just avoiding a vulnerable code pattern. And for OpenSSL HMAC, I didn't contribute any new code, except for a new test vector, but the code is the same because apparently the issue was already fixed. I did close the open issue that was there since 2020. So let me stop here and give time for questions. Thank you very much.
Thanks for a nice talk and your one-line contribution. You discussed the overflow in the possibly vulnerable pattern. Is there a potential for underflow now with the minus, or is it something that, I mean, I did not process it that quickly to see whether it's possible, but just like, have you considered underflow now?
Mm-hmm. Yeah, so if there's an underflow in the line that I corrected, then there's also an underflow on the line below, right? Because you have the same pattern appearing twice. So this C minus B is appearing twice. But of course, it could be that they're actually both underflowing, right? So this is something where you can apply tools to check whether your addition does not just overflow, also doesn't underflow. You can apply the tools to the example here and then see it's actually a bit trivial here. Whatever you have on the left side is always going to be larger than equal to what you have on the right side because of the way that variables are initialized. So you can prove by hand or using tools that there's actually no underflow.
Hi. The HMAC fix in 3.2 is nice, but 3.2 was not popular version across Linux distributions. Has that been backported to Ubuntu, RHEL, SUSE, Debian?
I'm using the latest OpenSSL, so if you're using older versions, you're yeah. No, I mean, I see what you're saying. What I'm trying to do with the test vector is to make sure that if people are using some older versions of OpenSSL, they can at least see that some of the tests are failing.
Thank you very much for the talk. I wanted to ask, if you're writing papers, typically the type of results you were showing us here, this is not what you are typically showing in the paper. Like you are coming with a methodology, you are coming with a tool that can automatically detect type of behavior. But then it seems that for the practical application of this academic result into OpenSSL code, you had to do like manual cherry picking and then fine tuning. Can you imagine that results of your academic work will be like the whole tool introduced into the pipeline of OpenSSL testing, or do you think it's way more practical and easier just to cherry pick some small parts and then by hand help to improve the code?
Well, I think it's a bit of both, right? So from an academic point of view, I think you want to have, as you're saying, a solid methodology where you say, here's a problem of one specific type, let's try to fix this all throughout, right? but then it turns out to be not so easy. Well, if you say that a certain sequence of calls is not allowed, well, the first question is that documented? It might not be. Do people agree that a certain sequence of calls is not allowed? It might not be. Would you like to, it would be nice to make a whole large document that contains every sequence of calls you can do and whether they're allowed or not allowed. That's, I guess, what you would like from an academic point of view. But that's not going to be so helpful if you want to work together with the OpenSSL project, because I don't think it's going to be helpful if I say, like, oh, here I have 1 million different combinations of calling the different functions. Tell me which one is allowed and not allowed, right? So I think you have to see how to prioritize. That's, I guess, what engineers are supposed to do, and see how can I have the maximum amount of impact when I want to point out specific issues that I'm trying to solve. And hopefully the solution will then eventually lead to more general fixes that are not just patching a specific issue. But I think it really helps to first fix a small example, and then you have a good argument to say, well, I can give you a few more examples, and then maybe I can apply a methodology.
I have a question. You demonstrated the examples of HMAC, of digest calls, update init update final. Do you expect that there would be similar vulnerabilities in the implementation of squeeze method, which is also popular for variable length hashes and KDFs?
It's possible. However, it seems that usually you will have more control over the message coming in, because the message coming in is, well, I can give you whatever digital signature that corresponds to a large message, and you could say, well, I never signed that. Doesn't matter. I'm asking you to verify it, and then you need to hash it to compute the signature. But if we're looking at the squeeze part, the protocol might already have fixed to say, I only squeeze a certain number of bytes out, and then the attacker doesn't have control over that because the application doesn't allow it. But it is, and you're right about that, a place where vulnerabilities might appear as well.
Okay, I have one more question. So with respect to the tooling, you mentioned CodeQL. In your research, are you using other tools or fuzzing or something like that? Because it looks like fuzzing might be useful, or maybe things other than CodeQL.
Mm-hmm. Yeah. So I'll answer very quickly because I know we're running out of time. When people try to apply fuzzing, the big issue is defining fuzz targets. And once you can do that, and that's the message I'm trying to send in my presentation, once you can define what exactly are the ways in which you can call your application that can cause the errors, then you can use any tool, which can be a fuzzer, which can be CodeQL, which can be certain tools used for program verification to prove with some SMT solvers in the backend that some overflows cannot occur. There's a list of tools that you can use. I am neutral with respect to the language, with respect to the tool. Tell me what your problem is, and I can tell you what a possible tool is to solve it. People have reached out to me to say, I'm using a different SHA-3 implementation. Do I have an overflow somewhere in my code? At the time, I didn't know how to answer that. Now I do, and I'm happy to share that knowledge with everybody here.